This presentation on alcohol distillation is made by Michael Holstrom and David Schultz, and we'll be talking about the importance of temperature sensors, the understanding of system dynamics, and the use of PID controllers. Overview and system assumptions. This PowerPoint will be covering alcohol distillation at the hobbyist scale. In later slides, we will be referencing mash, low wine, and high spirits, or spirits. Mash is the precursor and fermented solution that is used to initiate the distillation process. Usually only 8 to 12% alcohol by volume, mash usually contains the ingredients and recipe that is initiated for distillation, such as sugar, water, and yeast. Low wine is the distilled form of mash and usually contains 20 to 25% alcohol by volume. And finally, spirits or high spirits contains 60 to 70% alcohol by volume and is the distilled version of low wine. For this PowerPoint, we will be considering pressure changes to be negligible, since a normal and nominal run of a still will have little to no pressure change. Should there be any pressure changes, that would indicate a mismanagement of the system. And the still, being the focus of this PowerPoint, is assumed to have a filled tank of mash, indicating that once filled, there will be no more input during the distillation. This diagram shown contains the entire distillation system for making high spirits. On the left, the wash still, which will be the main focus of this PowerPoint presentation, followed by a warm box that cools and condenses the liquids down into low wine liquid form, then into the spirit still, which would then redistill the low wine into high spirit vapors, which are then condensed down in the second warm box to liquid form. Why is temperature regulation so important? The importance of temperature regulation using a PID and temperature sensors is to achieve the ideal steady state boiling temperature. Due to the many variables within the mash and still, it is very complicated to calculate. Therefore, adjustments must be made throughout the distillation process. These variables that change the boiling temperature include what kind of still is being used, the size of the still being used, the material of the still, what kind of heat source is being used to heat the still, such as wood, propane, or electric, the percent alcohol of the mash, and the recipe of the mash. All these factors can greatly affect the boiling temperature of the mash, as well as the different temperatures that will transfer throughout the process as the distillation cycle continues. The importance of temperature regulation with respect to safety. The temperature of the still must be monitored closely. The temperature of the low wine vapor, if exceeding the safe parameters, could indicate pressure buildup, which is dangerous, while the temperature of the mash exceeding safe parameters could indicate a burning of the mash, which would greatly affect the flavor and safe consumption of the final product. Finally, the importance of temperature regulation and monitoring with respect to flavor. Another key reason for monitoring the temperature of the still is to know what stage or cut the distillation cycle is in. The first cut or stage, known as foreshot or head cut, contains residue from the previous batches made in the still, as well as toxic methanol, which is not safe for consumption. The middle or heart cut contains the desired ethanol, which would be used in the final product. And finally, the final or tail cut tends to contain small amounts of oils and residues which could be harmful when consumed. Therefore, monitoring the temperatures and temperature differences between the mash and the vapors can indicate what stage in the cut you are in. There are two major components for the still, the inputs and the outputs. Of each, there are two inputs and two outputs. The first input being the mash itself. As the mash flows in, it is at a much lower temperature than the mash that's already in the still from the previous cycle. The second input is the heat source provided to the still at the base. For this example, we will be assuming electric-based heating. The first output is low wine vapors. This is a product that can either be consumed or condense down and flow into a spirit still, which can be refined to higher grade spirits. The second output is pot ale. Pot ale is what's left of the mash after the low wine and high level ethanol has been distilled and removed from the mash. We will also be looking at the specific sensors and system control used for the stills. Many stills come pre-equipped with two thermometers, the first being equipped at the base to read the temperature of the boiling mash. The second is set at the top, reading the heat of the low wine vapors, traveling up and out of the still into the spirit still. The top thermometer, if reading too high of a temperature, can indicate pressure building up. The lower thermometer, if reading too high of a temperature, can indicate a burning of the mash, which can greatly affect the flavor and safety of consumption for the final product. Another thing to note about the temperature readings is one can tell just by the temperature differences between the top and lower thermometer what stage or cut the alcohol cycle is currently in. To properly understand the need for thermal sensors and thermal controls of a wash still, we must first understand the heat transfer process in a wash still. The heat transfer process can be broken up into three major sections. The first section, at the bottom, can be classified as boiling mash. This is purely liquid and heats up the fastest due to its proximity to the heat source. The second region consists of boiling liquid mash and evaporating low wine vapors. And the third section accounts for the low wine vapors that are traveling up and out of the wash still. Now, because of the distance between sections 1 and 3, there tends to be, when starting up the system, a major thermal disparity. Now, when starting up a wash still, PID controllers become very important. Region 1 tends to heat up the fastest, therefore Region 3 tends to be much cooler when starting up than Region 1. However, eventually Region 3 will reach ideal temperature. By this time, Region 1 has exceeded ideal temperature, therefore the heat source must be removed or lowered. When doing this, the Section 3 will cool only slightly less than Region 1. Once Region 1 has reached acceptable parameters, the heat source can once again be provided and the process begins again, thus fluctuating, as shown in the generic transfer function graph. With each adjustment of the heat source, the fluctuation slowly decreases until eventually a steady state ideal thermal temperature has been reached to allow for a homogeneous boiling temperature throughout the entire still. PID controllers. There are many ways to control the temperature in the wash still. PIDs are the best combination of accuracy and speed for this application. A PD may reach a poor steady state or have a larger maximum overshoot, causing the mash to burn, while a PI controller might work too slowly, wasting time or affecting the flavor. Some brewers with enough experience even claim they monitor and control the temperature manually because they are faster and more accurate than a PID. This, of course, is all based on experience and personal preference. In conclusion, the importance of heat sensors and PID controllers together allows for a more accurate and quick steady state heat source to be applied to achieve a homogeneous temperature throughout the entire still. Heat sensors by themselves allow the user to detect what stage or cut the distillation is in and can warn of pressure buildup or burning of the mash. PID controllers are an excellent way to continuously monitor and adjust the heat source without manually having to achieve the steady state temperature. And these are the references.